Okay, so in the previous lecture, we were looking at one third order differential equation, and we were asked to verify that each function here is a solution to them. And actually, this is something very interesting because these three different solutions have apparently nothing to do amongst them when we compare them. One of them is exponential, and the other two are trigonometric functions. Also, we tested another function with three terms. That is the containing the multiple of an exponential, a multiple of the trigonometric, and a multiple of the other trigonometric, in this case sine and cosine respectively. All right, well, so this is actually the idea behind the superposition principle, which tells us this next theorem tells us that the sum or superposition of two or more solutions of a homogeneous linear differential equation is also a solution. Formally, what do we have? Okay, so if we have y1, y2, maybe y3, y4, y5, depending on the order of the differential equation, to be solutions to the homogeneous and order differential equation on an interval E, of course, we need to take into consideration the validity of the solutions. Then the linear combination C1, y1 plus C2, y2 plus etc. as many solutions as we have, where the coefficients C sub I are going to be 1, 2, 3, etc. all the way to k, all right, are arbitrary constant. That is also a solution to the differential equation. Okay, a consequence of the superposition principles is the fact that a multiple of the solution y equals c1 y1, which is also a multiple of y sub 1, will be a solution to the homogeneous differential equation. And finally, every homogeneous linear differential equation will always possess the trivial solution y equal to 0. We're going to talk about these technical definitions in a second. Well, so number one, what do we have? So it seems like these three are solutions with a coefficient equal to 1, or combinations of the three. The fourth function we tested, which is a combination of the three solutions, that's also a solution to the differential equation. Actually, this means that if we combine, so we could have done other, okay, let's see, letter E, for instance, y equals to 3e to the 2x plus 7 sine 3x plus maybe 0 cosine 3x. Well, actually, that's something we don't need to write. This for sure will satisfy the differential equation. I'm not going to do the whole process. You may verify it on your own and you will see how it's going to work. Maybe another one, F, maybe simply y equals to, I don't know, maybe 2025, 2020, oh, come on, 2025 e to the 2x plus, I don't know, 1970 cosine 3x. That's going to be another solution to the differential equation, or simply g y equals to, which is y equals to e to the 2x plus sine 3x plus cosine 3x. If you keep testing these other solutions, they will satisfy the differential equation. Notice the kind of examples I gave you. Notice I gave you cases in which the leading coefficients or the coefficients of the function are equals to 1, or other numbers, I mean, those also work, and that's the corollary that what you call that, a multiple of one of those solutions will also be a solution. For instance, if you go back to example to part A, okay, if you test y equals to 2e to the 2x or 5e to the 2x itself, that will also satisfy the differential equation. Also, let's talk about this trivial solution. The trivial solution, which is y equals to 0, is also a solution, but actually we really don't care that much about that solution because y equals 0, it's not a very interesting function. We actually that it's worth looking at. And I mean, just try it. So y equals to 0. So the first derivative, y prime, is also 0. Second derivative, also 0. Third derivative, also 0. Substitute 0 minus 2 times 0 plus 9 times 0 minus 18 times 0 equals to 0. So what do we have in this case? 0 equals to 0. So y equals to 0, which is called the trivial solution. That's also a solution to the differential equation. But again, as mentioned before, we really don't care about that solution that much. All right. Okay, so now what about more properties of these functions? Well, let's talk about the linear independence and linear dependence of these solutions. Well, a set of functions f1, f2, f3, f4, etc., f sub n is said to be linearly dependent, okay, on an interval, on some given interval, if there exists some constant c1, c2, c sub n, etc., not all zeros, such that, okay, a multiple of function 1 plus another multiple of function 2 plus etc., that gives us the zero function, all right, or the trivial solution, all right, for every x in the interval. On the other hand, if the set of functions is not linearly dependent on the interval, then that set is said to be linearly independent. All right. Well, so let's talk about this in a more in-depth fashion. Okay, well, actually, these concepts arise from linear algebra, but actually, okay, let me take a slight detour to linear algebra. Okay, so I'm going to talk about the vectors. I know this class is about functions that are solutions to the differential equations, but actually in a linear algebra course you will get to see that functions are also vectors provided they satisfy certain conditions. I'm not going to go over in detail about that topic. That's something you should cover in a linear algebra course. But to give you the bigger picture about this, well, so let's consider these three situations in which what do we have? Vector u plus vector v produces resultant vector u plus v, which happens to be, look at the tip of the vector, or the head of the vector. It has coordinates that are non-zero. So when we have two vectors that produce a non-zero vector, this set of vectors is said to be linearly independent. However, if we have two vectors that added together produce then the zero vector, notice the picture here. Notice we have the vectors kind of adding the other way around, producing a vector whose tip is in the origin. That's the zero vector. This set of vectors are said, these two vectors are said to be linearly dependent. That's the case we have right here. So functions, just like vectors, multiplied by certain coefficients or whatever, added together, if they produce the zero value, the zero function, well, those functions are linearly dependent. And well, the basic foundation comes from the fact with vectors. So actually, you will, in a linear algebra course, you will get to see this idea not just with arrows like this. Actually, other specific functions treated as vectors, matrices when they're treated as vectors, and many other mathematical other mathematical forms. Okay, so another case in which two vectors are linearly dependent is whenever we have one vector being a multiple of another vector. For instance, we can easily see here how vector u maybe has components 1, 0, all right? And well, if we observe vector v, okay, vector v seems to be twice the size of vector u. So 2 times vector u, which is 2 times the vector 1, 0, which is the vector 2, 0. Clearly, these two vectors, well, are multiples of each other. You can either say that vector 2, 0 is twice vector u, which is 1 0, or vector u, which is 1 comma 0, is 1/2 of vector v, which is 2 0. You can say it either way. So what do we have here? In any case, okay, these two situations are vectors that are linearly dependent. All right, well, so let me give you another real life situations in which you will see linear combinations. So think about your favorite fast food chains. Fast food chain. All right. Well, I'm not. No, yeah. Your favorite fast food chain. Think of that one. Okay. So what did you see in the menu? Well, typically you will see like either burgers or fries or drinks, some desserts, or sometimes you have combos. Well, those combos are combinations of fries, burgers, and soda, and maybe a drink, or maybe even a dessert. Well, for a simpler example, let's consider the set of vectors containing a burger labeled with a B, fries with an F, and a drink with a letter D. All right. So let's say you want to do combo number one. All right, but you want maybe small fries and small drink. Well, an invisible coefficient of one will represent the small fry and the small drink. Actually, well, I'm not going to use any coefficient on the burger here on the sandwich because they're usually the same size. All right. So there's no small or larger burger. They typically only come on one side. All right. So for instance, let's say you go to the I don't know to your favorite to that fast food chain. I don't know, and let's say you want your linear combo. Okay, you want your burger, you want a medium fry. Well, okay, I'm gonna multiply by 2 for the fry. All right, and you want a large drink. Okay, well, large drink, I'm gonna put a number 3 for large. So 1 is small, coefficient 1 is small, coefficient 2 means medium, and coefficient 3 means large. Okay, all right. So, okay, well, this is a linearly independent it's a linearly independent combo. Okay, well, another example, maybe you want, okay, another burger, or maybe you don't want the burger, maybe you just feel like a large fry with a medium drink. Okay, actually you don't have in your when you choose your run combo at your favorite fast food chain, you don't have to choose all three. All right, so maybe you just want fries and a drink. All right, this is also a linearly independent set of vectors. So the fries is a vector, the drink is another vector, but this time, well, if you want to be more formal, maybe you got zero burger. All right, you didn't get zero burger, but you don't have to. Okay, let's keep it large fries and a medium drink. All right, let's talk about a linearly dependent set of vectors at a fast food chain. Okay, so let's say you just feel like getting fries. So let's say you want a small fry and you want a large fry. All right, let's say the small fry is for your little sister or brother, and the large fry is for you. Well, in this case, what do we have? One of the vectors in the back at the fast food chain will be a constant of the other. This makes this set of vectors linearly dependent. All right, this makes us a set of vector that is linearly dependent. Well, what does this have? This very funky explanation having to do with solution to differential equations. Well, that's because when we have a fundamental set of solutions, this fundamental set of solution may be one or the other, independent or dependent. Well, how do we know if this is linearly dependent or dependent? Well, we need to obtain the Wronskian of the fundamental set of solutions. Well, so we have a set of n functions. Okay, so for the basic case, let's consider a set of solutions that has what's it called, three solutions, right? Three potential solutions. So that means this set must possess at least n minus one derivative. That is, in this case, we want to make sure that that set of solutions has at least the second derivative. All right, well, typically it will be the case. All right. Okay, so what about it? Okay, so to calculate the Wronskian, we evaluate this huge determinant here. So the Wronskian denoted uppercase W with parentheses, writing down function 1, function 2, function 3, etc. So the first row of the matrix will be the list of the functions. The second row of the matrix will be the first derivative of all these functions. The third row of the function will be the second derivative, and we continue until the n minus 1 derivative. All right, so if we have a set of solutions with five of them, then, well, we would need to calculate up to the fourth derivative, because the first row will be the original function, the second row first derivative, the third row second derivative, the fourth row third derivative, and the fifth row the fourth derivative. So we want to make sure these matrices are square, because the determinant is only defined for square matrices. All right, well, so we calculate the Wronskian. What about it? So how do we know if this how does that Wronskian tells us about the linear dependence or independence of these fundamental sets of solutions? Well, so let's have a look at the next definition. Any set y1, y sub 2, y sub n of n linearly independent solutions, okay, if that is, here we're already saying or assuming that this set is linearly independent of n order of the nth order differential equation on a given interval, is said to be a fundamental set of solution. But again, how do we know? This is known if the Wronskian is not equal to 0, just like the vectors here. If we get two vectors that added together in a similar way produce the 0 vector, we get a set of linearly dependent vectors. Same with functions. Here the Wronskian tells us that we value the Wronskian, and if the value of the Wronskian is equal to 0, well, these are going to be linearly dependent. And if the Wronskian is not equal to 0, then the set is linearly independent, and we say that we have a fundamental set of solutions. On the other hand, if the set is linearly dependent, this will not be a fundamental set of solutions. All right, we'll have a look at some examples about it. All right, okay, so now whenever we determine that a set of solutions is linearly independent, then we can write a general solution. So let's say y1, y2, y sub n forms a fundamental set of solutions to the homogeneous linear differential nth order differential equation. All right, on the given interval. Then the general solution of the equation on the interval is, okay, c1 y1 plus c2 y2 plus c3 y3 plus c4 y4, etc. So that's producing a non-zero solution, then a non-trivial solution. All right, as I would say. For instance, so this means that the solution to the differential equation in the preliminary example right here, in which the three of them, we're working with the three of them, well, we can write the solution as y equals to c1 e to the 2x plus c2 sine 3x plus C3 cosine 3x. All right. So where C1, C2, C3 are going to be different coefficients, like the coefficients we chose, you can put your favorite number. And in this case, well, to keep things simple, I chose just integers for C1, C2, and C3. But of course, these coefficients can be 1/2, square root of 7 over 19, or e cubed divided by the cube root of pi, or something like that. It should also work. All right. Okay, so now let's have a look at one example, well, a couple of examples actually. So the set of solutions e to the 3x comma e to the negative 3x are solutions to this differential equation. For now, just take this for granted. We do not have at this point, we do not have the knowledge to solve this differential equation, but we will soon, okay? So they're asking us to show that the functions form a fundamental set of solutions. How do we know? If they are linearly independent. How do we know if they're linearly independent? If we compute the Wronskian, and the Wronskian is not equal to 0. Okay, so let's denote the Wronskian to be W of e to the 3x comma e to the negative 3x, and that equals, okay, the first row will be e to the 3x, the set of solutions, e to the negative 3x, and the second row will be 3 e to the 3x, negative 3 e to the negative 3x. Okay, so let's evaluate this determinant. Okay, so to evaluate a 2 by 2 determinant, all we need to do is multiply the elements along the main diagonal, that is the element 1 1 element with 2 2 element. Okay, that is e to the 3x times e to the negative 3x, and we will subtract whatever we get from multiplying the elements along the secondary diagonal, that is the element 1 2 and 2 1. In this case, oh, I forgot to multiply by negative 3 here. Whoops. Okay, let me change this. Negative 3 e to the negative 3x, okay, minus e to the negative 3x times 3 e to the negative 3x. Okay, so the rest of the problem is just simplify and make sure we don't get 0 at the end, to show that the set is linearly independent, and therefore it's going to form a fundamental set of solutions. And this is positive right here, right? Plus 3x. Okay, so what is this? So e to the 3x minus 3x, is that equal to e to the 0, which is 1, right? And over here, e to the negative 3x plus 3x is e to the 0, which is also 1. And this is negative 3 minus 3, which is negative 6. Whatever that is, because this is not equal to 0, therefore the set e to the 3x comma e to the negative 3x forms a fundamental set of solutions. Why? Because the Wronskian, the determinant described that calculates the Wronskian, is equal to 0, which means the set of functions right here is linearly independent, and because a set that is linearly independent is said to form a fundamental set of solutions. Yes, this is the same idea as with vectors in linear algebra. Well, it's the same idea with functions here. All right, well, let's have a look at one more example. Okay, example number 3. Let's do a 3 by 3 one. All right, this one is going to be fun. It's going to be an interesting one to do. Okay, so same. Show that the functions given in the set form a fundamental set of solutions. So that means we need to compute the Wronskian of e to the 2x cosine 3x, sine 3x. Okay, so what are we going to do? We're going to write down a 3 by 3 determinant this time. Well, where the first row will be the functions e to the 2x, cosine 3x, sine 3x. Okay. The second row will be the derivatives of these functions. 2e to the 2x, negative 3 sine 3x, and 3 cosine 3x. The third row will be the second derivatives, that is 4e to the 2x, negative 9 cosine 3x, and negative 9 sine 3x. Okay, so this time we have to evaluate a 3 by 3 determinant, and well, there's a few ways to evaluate a 3 by 3 determinant. Well, number one, well, if we were in a linear algebra course, well, then we have a couple of techniques, a couple of strategies. Number one, expanding this by cofactors and minors, or number two, using elementary row operations and this to reduce the 3 by 3 matrix into a 2 by 2 matrix. That's another one, but that's actually very time consuming. There is a third rule, not often covered in many linear algebra courses. It's called Sarus rule. That's actually a technique I use in calculus 3 to compute the cross product between two vectors, which is actually it actually deals with a 3 by 3, the determinant of a 3 by 3 matrix. And this rule I'm going to show you only works for the 3 by 3 case. So, okay, have a look at this. Okay, the way we go about this is by repeating the first two columns. Okay, let me copy and paste. I'm a little lazy to rewrite. Okay, and this is what we're going to do. So just in a similar way that we did the 2 by 2, I'm going to use green arrows to multiply all the elements along the main diagonals, like this. Whoops. So like this, like that, and like that. Okay, so let's see what we get about this product. Okay, so this will be equal to negative 3 times negative 9 coefficients first, that's 27 e to the 2x, sine times sine, that's sine squared 3x. And then what do we have? Plus coefficients first, 4 times 3 equals to 12. Okay, I'm going to write the exponential first, e to the 2x, and then cosine times cosine, that's cosine squared 3x. All right, minus, I think, negative 9 times 2 is that 18 e to the x, or rather e to the 2x, sine times cosine, careful with this one, sine 3x cosine 3x. All right, so that's our result of the multiplications along the arrows that go from left to right. Let me use a different color for the second part of the problem. Multiply this 3, multiply this 3, and multiply this 3. Okay, so I'm going to subtract. However, be careful when subtracting, open parentheses, because this subtraction will affect these three operations we're going to do. Okay, so 2 times negative 9, what is that? Negative 18 e to the 2x. What do we have? Cosine times sine, that's sine cosine. We write sine 3x cosine 3x. Okay, and then e to the 2x. Okay, that's 3 times negative 9, that's negative 27. Okay, negative 27 e to the 2x, and that is cosine times cosine, that's cosine squared 3x. And finally, negative 3 times 4, coefficients first, negative 12 e to the 2x, sine times sine, that equals to sine squared 3x. All right, so Well, let's number one. Actually, I'm going to distribute the negative sign. Well, you know what? I think I'd rather highlight. That's going to help us see all the terms we're going to end up with and what we can cancel and combine. Okay, so all the terms containing cosine squared. Well, let's start with sine. All terms containing sine squared, I'm going to highlight them with this color, okay? So, oh, I forgot to close the parentheses. Okay, yes, this one. Okay, I'm going to use yellow for the ones containing cosine squared, and cosine squared. And lastly, with a different color, I'm going to use green for all terms containing sine cosine. All right. Okay, so actually we can easily see that negative 18 e to the 2x sine cosine with negative positive cancel out, okay, and that actually can't all those two terms go away. Now the terms containing the sine squared, what do we have? A 27 in the coefficient, and then we have what is that? A negative 27, but this a negative 12. Okay, negative 12. However, this negative 12 right here becomes positive because of the negative outside. So what do we do? Add 27 plus 12 plus 27, that equals 39. 39 e to the 2x sine squared 3x. What about, okay, so actually let me put a mark on this that I already combined them. And finally, let's combine the cosine squares. Okay, so same actually, negative 27 with a negative outside, that becomes a positive 27 plus 12. That's another 39 e to the 2x cosine squared 3x. Okay, well, actually, let's keep simplifying this. If we factor out 39 e to the 2x, that's going to leave us with sine squared 3x plus cosine squared 3x. And well, that actually spawns one of the most important identities in trigonometry, the Pythagorean identity, which equals to 1. And our final result equals to 39 e to the 2x, which actually this is not equal to 0. The fact that our determinant is not equal to 0, well, that means we have a linearly independent set of functions, which means the set e to the 2x sine 3x cosine 3x, which, by the way, this is actually the same set of solutions from our preliminary example. So this is, or rather forms, a fundamental set of solutions. All right. Well, even though we don't have anything else on the notes, okay, let me show you an example of how something would not be a fundamental set of solutions. For instance, let's see, let's do the, okay, so example 4, okay, let's try e to the 2x and 3 e to the 2x, okay, something like this one. Alright, well, actually by looking at the functions, you can already tell that this is not going to be a fundamental set of solutions, because this set is not linearly independent. It's actually dependent, because one of the functions depends on the other function, because one of the function is a multiple of the other function. All right, actually it's like the example I give you on the fries, you know, on the fast food chain. What do we have? A small fry here and a large fry? Well, that's a dependent linear, a linearly dependent set of functions or vectors if you want, all right? But see, let's compute the Wronskian for this one. That is w of e to the 2x, comma, 3 e to the 2x. That equals the determinant of the first row, e to the 2x, 3 e to the 2x, and 2 e to the 2x, 6 e to the 2x. Okay, let's compute the determinant. Okay, so elements along the main diagonal get multiplied to give us e to the 2x times 6 e to the 2x minus product along the secondary diagonal, multiply 3 e to the 2x times 2 e to the 2x, and that's going to give us what? 6 e to the 4x minus 3 times 2, which equals 6 e to the 2x, which actually equals to 0. Oh, so because in this case is that the Wronskian equals to 0, this set is linearly dependent. Therefore, e to the 2x, 3 e to the 2x does not form a fundamental set of solutions. And I think this is a good place to quit.